So last week I introduced Lewis structures, and Lewis structures are an illustrative method. They're just basically a kitty drawing, a stick figure with dots, okay, drawing and letters of how covalent shared electron bonding works between typically non-metals, okay, that right side of the periodic table. Non-metals and metalloids, because metalloids, they look like metals, but they act like non-metals, right? They're that kind of unique combo. So between metalloids and non-metals, or non-metals and non-metals, that's what we were talking about, the sharing of electrons. And that is, by the way, for the project I'm going to introduce in a second. Not a, the cheat sheets are over there by the periodic tables, extra copies in that tray set. Okay, so that's where we left off. And I introduced the exact process of how you should go through drawing a Lewis structure, okay, to make sure everybody has their duet or octet and that you've used up all the possible valence electrons, all right? And of course, I also went through a couple exceptions where we talked about, well, there are some molecules that don't have even numbers. Therefore, there's always going to be one, what do we call it? Single electron. What do we call that? A radical, like the lone wolf, right? A radical. So we also talked about times when we have more than 8 electrons being shared with an atom. And those are possible with elements in row energy level 3 or above. Because now when you get to row 3, energy level 3, you have 3D, 4D, 5D, 6D, 4F, and 5F, which tells you that you have all these empty pockets where you could hold more, which is why certain elements in row 3 or above can hold more electrons than 8 as the center atom, which also tells you why some noble gases are actually reactive, even though generally speaking, we introduced in unit 2 that they were not reactive. But there are special cases when they must step up, okay, to the call, right? So you guys were challenged over the weekend for homework to complete some of these problems on your own, okay, where you had special cases, okay? Please get out your periodic table, your Lewis structure cheat sheet, and your notes. So let's look at this first one. What is step 1 always? Total valence electron. So total valence electron count is each chlorine brings 7. How do I know that? Well, I look at my periodic table and I say chlorine is in the 3rd row. So the boxes representing a place where electrons are, okay? I have 1, 2, 3, 4, 5, 6, 7 boxes, including chlorine's box, that I must fill in the outermost row, the highest row, the row it exists in. Those are my valence electrons. 7 out of these 17 electrons are going to be placed in energy level 3, okay? The highest energy level for chlorine. So, and I have 2 oxygens, ClO2 minus. So I have 2 oxygens. I have 1, 2, energy level 2. Okay, 1, 2, 3, 4, 5, 6 of those boxes in energy level 2. So 6 out of the 8 electrons are valence electrons existing in the highest energy level, represented through the periodic table. Okay, so I say I have 7 plus 6 times 2, which gives me a value of 19. Automatically, you know something's going to go down. Like there's going to be a radical somewhere, okay? So we create our structure. Here, we actually have halogen be in the middle, okay? Because it's written first, and there's 2 oxygens. And usually if you have a repeat of a compound, right, multiple of them, they tend to be around. So it's chlorine, okay, bonded to 2 oxygens. Now, how many electrons? Now I need to track. I drew my skeleton structure. How many electrons did I just use up to make them? Yes, 4. To make the minimal amount of bonding, 2 and 2 shared. So now I'm left with 15. So now what do? What, Liam? I distribute the remaining electrons to my terminal outer atoms, my non-central atoms, right? Terminals, airports, outer, okay? Think about the legs of a spider, all right? So I say, well, oxygen currently has access to 2. I'm going to start with my left oxygen just because. So I'm going to give it 6 more to give it its octet. 6 of its own plus 2 shared, giving it access to 8. Okay, so I do -6. I have 9 left. 1, 2, 3, 4, 5, 6. I deal with my other one. Okay, -6. I have 3 left. Now I look at chlorine. I'm done. I'm octetted it out for my terminals. Now I look at chlorine and I say, how many does chlorine currently have access to? 4. How many more does it want, theoretically? 4. What do I have left? That's all it is going to get. That's it. It's going to be okay. I mean, it doesn't really have a choice. Now, you could argue, well, would it be better to be under 8 or over 8? Should I double bond one of these oxygens to it? Because chlorine is technically row 3 or above. But what do we know about halogens? They never make double and triple bonds. And chlorine is a halogen, column 17. It does not ever want to make a double or triple bond. So we know that for chlorine, it would rather be 1 under than 1 over to avoid making a double or triple bond. Okay. Okay. So beryllium difluoride, total valence electron count. What do we got? So 4 plus 7 times 2, giving me 16. Then why did we say 16? Oh, 7 times 2 is 14. Jokes. Okay. Whoa, 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 gee willikers. Okay. I have not left school. I've been at school multiple times this weekend. So I think I'm just like maxed out on school right now. Okay, 16. 16. So now we put our structure. First element is usually the center, unless what? What's never a center? Hydrogen and helium. Excellent. The two that can literally only make a single bond and then they're out for the count. Like they're just done. Okay. So we got beryllium in the middle and the 2 fluorines. Okay. How many did I just use up? So how many do I have left? Thank you. Okay. Let's start making our octets. Okay. That is 6 minus 6, giving me 0. Okay. Beryllium only has access to fluorines are good. Does beryllium need more? Do we need a double bond? It doesn't need more. Also, you're partnered up with 2 fluorines. Fluorines are what type of element? Halogens. What do halogens never do? Double or triple bond. So you kind of know that beryllium low-key kind of has to be okay with 4. But we know from our rules that beryllium is okay with 4 or 6. Same with boron, same with aluminum. They don't have to have 8. Especially if the atoms that they're partnered with, fluorine, don't ever want to make a double or triple bond. Kind of just forces you to be okay with it. Okay. How about iodine tetrachloride? Okay. Total valence electron count. Notice this is a polyatomic by itself. A polyatomic molecule by itself is covalent. It is covalent. Only when it's bonded to another ion is it ionic. But it is naturally covalent. Okay, so total valence electron count is 7 plus 7 times 4, but wait. I have a -1 over or a 1 minus overall across the entire molecule. So that's like saying for my entire molecule, I have what? You have what? Gained 1 electron, gained 1 extra negative to push my neutral over. So now I'm going to say it's like I've added an electron. So now my total is 7 plus 28, 35 plus 1, 36. Now I start distributing. I build my skeleton. I is in the middle. I've got 4 chlorines. I won't write it like that because that's going to confuse you. I'll write it like this. Okay. And I'm going to say, how many did I use up just there? 8, 2 for every bond I made. So I'm down to 28. Okay, now I'm going to distribute one at a time to my terminal. 6, 6, 6. Can I do just 2 in a row, please? Okay. Okay. Now I have 4 left. Does chlorine want to take on any more? Any of the chlorines? So we have iodine. Okay, iodine. What does it currently have? 8. It currently has 8, but we have 4 left. So question is, who has a bigger stomach? Who can handle it? Well, where is iodine? What energy level is iodine found in? Row 6, energy level 6, which means it has access to a 6D. So what can we do? Where can we put those extra electrons? On iodine, on iodine. Confidence, people. It's all about confidence. Even if you're wrong, just be confidently wrong and then just accept it and then move on. Okay, so iodine gets the last 4 because it can handle the expanded octet. So iodine now has access to how many electrons total? 12. 4 of them its own, 8 of them shared. And it's okay with that. Okay. And that is the structure. Now, what am I missing? Yes, Mary. You need to put brackets around it because it has a charge. Yeah, I need to put brackets around it because there's no way I could make this structure without having that extra charge. It would not be the same structure. It would be one less, right? It would have a radical if I didn't have that charge. All right. So, honors, you are going to be tasked the struggle of wrestling through the idea that when following my Lewis structural rules, sometimes you get a variety of Lewis structures still for the same compound that are all technically valid according to the rules. So you're going to be going through what we call resonance, different valid Lewis structures for the same molecule, and then assigning what we call formal charges that are fake charges to help determine which structure is the most likely to appear in the world, right? If we have a variance amount of possible structures for the same compound that, again, follow all the rules, well, how do we know which one is going to be the most likely? Okay. That's where formal charges come into place. And there are a bunch of rules that you have to memorize with how to assign the formal charges and interpret them so you know which structure is most likely. That is honors task. And that can be found on my website and my Canvas. The link to the video, it's kind of longer. It's like 20, 25 minutes. You're gonna need to submit proof of notes at the very least, but you definitely should just be doing workbook problems in general on your own. Now, that's the honors task, but everybody has an additional project that they're gonna get time to work on today and tomorrow. And that project is, let me show you. And I totally forgot to download it. Hold on. It is called, you guys can pull it up on Canvas. It is called Flip a Clip, and there's a physical copy here in front of you. Flip a clip and a physical copy here in front of you. Okay, so this is what I'm going to say. This is a bit of a time-consuming project, and here's why. The goal of this project is you're going to create an animated tutorial on how to draw a Lewis structure, following the exact rules I gave you in that exact order, using the app Flip-a-Clip, which is basically like clay animation, but digitally, okay? And you're going to record a voiceover that describes each process as if you're a teacher explaining every painstaking step. You're going to go into the teacher role and you're going to say, first, you have to count total valence electrons. This atom brings this many. This atom brings this many for a total of this. Next, we're going to do a skeleton structure. This atom is connected to this atom because we know this is the central. Next, we're going to calculate how many we use, and you're going to articulate every step with clarity, succinctly, but detailed. You know, it's like a little oxymoron, okay? So it is not easy to not skip steps. You're going to have to force yourself to slow down in your thinking, especially if you're getting comfortable with it, okay? But the goal is you're going to draw 2 molecules and you're going to work in partners, okay? You're going to draw on 2 molecules, okay? One has to have a multiple or double bond, like some double or triple bond. I'm going to force you to deal with special cases. One must also be a polyatomic that you draw, where you have to account for the gaining or losing of your overall electron count. Okay, so your 2 molecules must have a double bond or triple bond and must be a polyatomic. So each partner will take on 1. Okay, your Lewis structure, so each molecule must have at least 3 atoms. Do not do like CO, carbon monoxide. Like that's not enough. So like CO is a CO is a no-go. It's got to be at least CO2, which by the way is a great double bond one. It's got to be at least SO3, which is another double bond one, potentially. It's got to be HCN, okay? Although we've done that for a practice problem, so that's a no-no. You can't use any of the practice problems that we've done in class. It's a no-no, okay? So it's got to be at least 3. You should write a description. You should vocalize a description of each step. Be sure to include relevant vocabulary. So you should be using the term central, right? I put it all down here. Central, valence, covalent, single, double, triple, terminal, octet versus duet, charge, polyatomic, and honors. You might need to talk about resonance structure. Okay. You want to narrate each step. And if you use the app, it is interesting to try to align your speaking with the animation. So you're going to have to figure that out with your team member. The animation should be relatively smooth. And my biggest tip is do not forget to use copy and paste, because you just want to be changing 1 clip at a time by 1 feature. You don't want to be redrawing each clip, right? The idea is that it transforms by a single or a couple elements each time. But the timing is a little bit of a pain with the speaking. Has anyone used Flip-a-Clip before? A couple of you. Okay, you might need to be on duty to help. Yes.
Just as a rule of thumb, Flip-a-Clip, it automatically sets you at 12 frames. I would recommend not doing 12 frames. It's way too fast.
Yes. So if you look at the bottom, thank you. If you look at the bottom, digital people, there's a walkthrough video that my previous TA from last year put together. It is not perfect. It does not meet all the qualifications, but it gives you an idea how to work the Flip-a-Clip app. But there is detailed instructions down below. You should probably using 3 to 4 frames per second. It slows it down. Maybe even some did 1 to 2, just because of how long the partner talked. There's a bunch of instructions, and the big idea is that you download this as a movie. Please make it a movie. Do not try to send it to me through Flip-a-Clip. It's not going to work. You're going to make a movie and submit it onto Canvas. Your team member will tell me as well, you should write as the title who you're working with, okay? So that I look at both of your guys' Flip-a-Clips, however you distribute the work, and I give you guys the same score. Unless, by the way, and I totally encourage this, you tattletale. Here's why I encourage tattletaling. If you get stuck with a partner that did nothing, you did basically everything, and they get the same score as you, that's bull. You can tell me in comments, I worked with this person and they did nothing, and maybe they had a reason. Maybe I need to talk to them about something that's going on in their personal life, but they do not deserve the same score as you. So while you put their name on it, and you need to all put your partner's name at the beginning. Okay, please do not give credit where credit is not due. If they did not do it, they do not get the same score as you. And that's the deal. There's going to be plenty of times in life where people write off your success and you write off of the others. This is not one of them. Okay. So for those of you that are hoping to write off of a partner, say goodbye to that. Okay. And do not feel bad about tattletaling. Like I said, you will be run over plenty of times in the future. You do not have to be run over today. Okay. So, now, one final thing I want to say about this animation is this, since it is so time consuming with the app, I will give you an alternative. You can also do this via comic strip paper, where you draw it on Notability. Okay, but the idea is that it should almost flip too. So maybe you create slides where as you click, okay, your images show the transformation, or you scroll. Okay, I don't know how you want to do that exactly, but I do realize for some people doing it by hand might be easier. But the idea is the same. You should kind of draw out each step. Now, you don't have to add each electron dot one frame at a time. You can add groups of electrons one frame at a time. Okay, so that's totally fine. But I should not see you jump from skeleton to completed structure. Like, that's not the point, right? So keep that in mind when you're either drawing this out physically or digitally, or you're using Flipbook. But physical people, you need to keep in mind, you still need to have narration. So you still need to do an audio recording over it and create a movie somehow. So it's all still going to be digital as the final product, but you can go through a slightly different physical method in the beginning if you want to for the drawing. Yes.
So we could do like Google Slides and then it's iMovie and do a voiceover.
Yep, that is totally fine. So honors, you've got a lot to do. You got your video, you've got your project. Prep, you've also got a lot to do because your project. Okay, yes.
Should we do the project with the new stuff that we learned in the video?
I am not going to force it.
Okay.
So I wanted to give you guys a little bit of flexibility, but honors, it would probably help you understand it better.
Do the video and then...
It would be helpful, but it is not essential. And keep in mind, you will have today and tomorrow, and Wednesday you will be quizzed on Lewis structures, because the idea is after doing this project, you will understand Lewis structures so much better. All right, guys, good luck.